In the last lecture, we talked about the expectation of a random variable, which is a first-order statistic of the distribution. A second-order statistic that we frequently use is the variance. The variance of a random variable x is defined as the expected value of x minus the expectation of x. Essentially, it is the expectation of the square difference of x from its mean. In other words, it's the expected deviation, squared deviation from the mean. You can easily manipulate this expression, expand it, and regroup using the linearity of expectation to show that this is equivalent to the expected value of x squared minus the expectation of x squared. We often use this form or this form depending on which one is convenient in the given computation at hand. Now, what happens when we take two random variables and add them and compute the variance of the sum? Now, you may say that when we add two random variables, the randomness increases. That intuition is generally right, except it depends on how related these two random variables are. Okay, now by plugging in x plus y to this expression and rearranging the terms, you can easily show for yourself that the variance of the sum of x plus y is nothing but the variance of x plus the variance of y minus twice the expectation of x minus the expectation of x times y minus the expectation of y. Now this thing, the expected value of the product of the difference of x from its mean and the difference of y from its mean, is also called the covariance of the random variables x and y. Now, if the covariance of x and y is 0, we say that the random variables x and y are uncorrelated. You may have heard of this in daily life. When people say two things are uncorrelated, they usually mean that how big one is does not give us information about how big the other one is going to be, etc. So uncorrelated, the technical definition of uncorrelated means the covariance is 0. When the covariance is 0, if you look at this expression, you'll see that this term will go away. So when x and y are uncorrelated, in this case, variance of x plus y is equal to the variance of x plus the variance of y. So when the two random variables are uncorrelated, really the variances add. The total randomness in the summation is the sum of the variances. The randomness adds in the sense that the total variance of the sum is the variance of one plus the variance of the other. Now, there are cases where it is going to be less. For example, if x and y are linearly related, we have a different situation. So now, this means the variance of the sum being equal to the sum of the variances is true if and only if x and y are uncorrelated, particularly if x and y are independent then clearly expectation of x minus expectation x times y minus expectation y breaks down into the product expectation x minus expected x, expectation y minus expected y, but both of these terms are 0. So this means when x and y are independent, x and y are uncorrelated as well. So independence implies uncorrelatedness. The converse does not hold. The converse is not always true. So let me give you an example, in fact, of two random variables that are uncorrelated but not independent. Suppose x and y have this continuous joint distribution that is constant on this rhombus. Suppose it's a minus a, okay, and fxy, xy, the joint density is equal to a constant in this region. Now clearly by inspection the expectation of xy is 0 and the expectation of x is 0. Why? Because x times y takes these values, these positive values here and the same negative values here with equal probability, and similarly there and there. Okay, so expectation of x is 0, expectation of y is 0. Clearly then the covariance of x and y is 0. So they're uncorrelated, but they are not independent because, you know, for example, if x takes the value a over 2, y can take values from negative a over 2 to a over 2. But if x takes the value 0, y can take values from negative a to a. So the distribution of y is influenced by the value that we set for x. That counterexample shows that they are not independent. Okay. Now let's talk a little bit about a few properties of variance. Variance of a scaled version of a random variable. By the definition, you can clearly show that this is c squared times the variance of x. So if you add x and x together, the variance does not increase by 100%. It increases by 300%, right? Because you are adding the randomness in x to itself, essentially the variance. You know, there's no quantifiable randomness. So let me take this sentence back. But if you basically multiply a random variable by 2, the variance is quadrupled. Right. Now, the variance of a random variable being 0 implies that the random variable is just a constant with probability 1. Okay, so that's a useful fact that can be shown, that we won't spend time on. The square root of variance is called the standard deviation, usually denoted by sigma. And we define a correlation coefficient for two random variables x and y as the covariance of the random variables normalized by the product of the standard deviations of the random variables. And this covariance always lives between negative to positive 1. And the covariance of two random variables is 1 if and only if one random variable is obtained by a linear scaling of the other.